All right, so we're doing our last section for this unit on sequences and series, infinite geometric series, section 1.5. And just a reminder that when we talk about an infinite geometric series, we're talking about an infinite number of numbers that we will be adding together. Okay? There are two kinds of infinite geometric series, convergent and divergent, so we will take a look at those two, and then we're going to take a look at how to derive the formula for an infinite geometric series. Okay, so a convergent series is a series with an infinite number of terms in which the sequence of partial sums approaches a fixed value. Okay? A series for which r is between -1 and 1. Okay, so the way we write this is we go -1 is less than r, which is less than 1. Okay, you should memorize that. Okay, what that means is that the value of r is between -1 and +1. Okay? So when we're talking about a convergent series, that's one of the conditions. R has to be between -1 and 1. The investigation provides an example of a convergent series. So the investigation is the one that you did in class last day. Okay, so I will just remind you of what that was over here. Okay, so you should have gotten a series of 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. Okay, which would give you 0.5 plus 0.25 plus 0.125 plus 0.0625. Okay, and the sums would go on forever. Okay, so let's take a look at the example that we're given here, and then we'll take a look at our investigation example. Okay, so consider the series 4 plus 2 plus 1 plus 0.5 plus 0.25. Now notice that the numbers, or the terms in your series, is going down in value, right? It's from 4 to 2 to 1 to 0.5 to 0.25. Okay, find the sums of the first 5 terms. So if we add up these first 5 terms, we will get 7.75. Okay, what if we add up the first 7 terms? Then you're going to get 7.9375. The first 11 terms, 7.9961. The first 15 terms, 7.9998. Okay, so what do you notice about these numbers? They are getting closer and closer to what value, to what number? You should notice that they're getting closer and closer to 8. So as the number of terms increases, the sequence of the partial sums approaches a fixed value of 8. Okay, notice that. It's getting closer and closer to 8. Therefore, the sum of this series is 8. This is another example of a convergent series, okay, because the first one that you looked at was your investigate. All right, so let's take a look at this one here. The sum of the first 4 terms, okay, I worked out to be 0.9375, and then the first 5 terms I worked out to be 0.96875. Okay, and then the first 7 terms I worked out to 0.9921875. Okay, so ask yourself, what number are we approaching here? And hopefully you're thinking that we're approaching 1, and the answer is yes, if you got that. So the sum of this series is 1. Okay, and you would expect that because you were taking a piece of paper and dividing it in half, and then in half and half and half. So because you have one sheet of paper, you would expect that the sum of all these parts would add up to 1, which would represent your one sheet of paper. Okay, so let's take a look at Divergent. series. So a divergent series is a series with an infinite number of terms in which the sequence of partial sums does not approach a fixed value. This is a series for which r is greater than 1 or r is less than -1. Okay, in other words, r is not between -1 and 1 this time. It's on either end of that. So it's going to be less than -1 and greater than 1. What you should notice about these series is that the numbers will get bigger. Okay, so 4 plus 8 plus 16 plus 32. So 4 to 8 to 16 to 32. The numbers are getting larger and larger and larger. Okay, so let's take a look at this. The sum of the first two terms is 12, right? 4 plus 8 is 12. The sum of the first three terms is 28. So 4 plus 8 plus 16 should give you 28. The sum of the first four terms is 60. 4 plus 8 plus 16 plus 32 should give you 60. And if you were to add up the first five terms of this particular series, you would get 124. Okay, so what do you notice about the numbers? The numbers are getting larger and larger. Okay, so the more terms that we would add up on this, the larger our number would get. So as the number of terms increases, the sum of the series continues to grow. The sequence of partial sums does not approach a fixed value. Okay, and that's because the numbers are getting bigger and bigger and bigger. Therefore, the sum of this series cannot be calculated. This series is said to be a divergent series, okay, because there is no fixed sum. We're going off into infinity, okay? All right, so what you should have figured out from our two definitions is that you can actually find the sum of a convergent series, but you cannot find the sum of a divergent series. So what formula do we use if we want to find the sum of a convergent series? Okay, so we're going to derive that formula, and we're going to use something called an intuitive proof. Okay, so we're just going to reason it out. Okay, so you already know that the formula for your geometric series for the sum of that is s subscript n equals t1 times 1 minus r to the n over 1 minus r. And so what we're going to take a look at is what happens as n, our exponent here, becomes a very large number. Okay? So as n gets very large, the value of the r to the nth power approaches 0. Okay, for values of r between -1 and 1. All right, so what does that mean? Well, as an example, or an illustrative example, why don't we just say that r is 5? Okay, and I'm just picking that number out of the air. That means that r to the n will be 5 to the n. Now, let's see what happens to r to the n as n gets to be a very large number. Okay, so we've got, sorry, this should be 0.5 because we want r values between -1 and 1. Okay, so 0.5 to the n. Okay, so why don't we just say that n is 2, and we're going to raise 0.5 to the second power, and you will get 0.25. Let's increase the value of n. Let's say that n is 10. And we raise 0.5 to the 10th power. You would get 0.009765. Let's make n even bigger. Let's say that n is 20, and we're going to raise 0.5 to the 20th power. So you're going to get point, and then you're going to get 6 zeros. So 1, 2, 3, 4, 5, 6, and then 9, 5, 3, 6, 7. So what do you notice about your value of r to the n as your exponent n gets larger and larger and larger? You should be seeing that this number is becoming very small. Okay? So it becomes so small that for all intents and purposes, we can say that the value of that is 0. So r to the n approaches 0, and it becomes such a small number that we are actually going to say that it's equal to 0. Okay? So as n gets large, the partial sum at s subscript n approaches t to the 1 over 1 minus r. Okay, well, why is that? Well, as we just said, as r to the n, as n becomes larger and larger and larger, r to the n approaches 0. Okay, and as it approaches 0, we're just going to say that it is equal to 0. Okay? What that means is I can now replace the r to the n with 0. Okay, so my new formula is going to look like this. T to the 1 times 1 minus 0 over 1 minus r. Okay, and 1 minus 0 is just 1. So s subscript n becomes t to the 1 over 1 minus r. Okay, because 1 minus 0 is 1, 1 times t to the 1 is t to the 1, and we have 1 minus r in the denominator still. Okay, so that's where this comes from. All right, it's the same as this. Okay, so therefore the sum of an infinite geometric series is s infinity, s subscript infinity, equals to t1 over 1 minus r, where negative 1 is less than r, which is less than 1, and r cannot be equal to 0. Now, we discussed why r is not equal to 0 in our last lesson, and that's because if our common ratio is 0, even though we would have a first term that would have a numerical value other than 0, the second and the third and the fourth and the fifth and so on terms would all be equal to 0, and we would no longer have a geometric sequence or series. Okay? So the sum of an infinite geometric series where negative 1 is less than r, which is less than 1, which should remind you that we're talking about a convergent series, can be determined using the formula s subscript infinity equals t1 over 1 minus r, where t1 is the first term of the series, r is the common ratio, and s subscript infinity represents the sum of an infinite number of terms. Okay, and so that concludes our introduction to infinite geometric series. All right, so example 1. Determine whether an infinite geometric series is convergent or divergent. Okay, so just remember that a convergent geometric series means that you can calculate a sum for it, okay, and the value for r is between negative 1 and 1. Okay, so that's convergent, meaning you can find the sum. And divergent, meaning that there is no sum, okay, and that means that r is greater than 1 or r is less than negative 1. Okay, and you really should memorize those two pieces of information. Okay, so one way to recognize them is if you have a divergent geometric series, the numbers should be getting bigger and bigger. And if you have a convergent series of numbers, they should be getting smaller and smaller. Okay? So what we're going to do, we're going to calculate the value for r and then make our decision. But you can't decide that by just looking at them. So the first one you should know intuitively is divergent, and the second one is convergent. The numbers are getting bigger here, so it's divergent, and the fourth one, the numbers are getting smaller, so it is convergent. Okay? All right, so let's figure out the value for r on A. So r is equal to t2 over t1, so 10 over 5, which is 2. Okay? So if we take a look at our conditions for r for a divergent geometric series, this is a situation where r is greater than 1, right? Because 2 is bigger than 1, so it fits into the condition for a divergent geometric series. So this is divergent. Okay, and on the second one, the value for r, t2 over t1, 2 over 4 is 0.5. So this r value is between negative 1 and 1. Okay, so it is convergent. And this third one, the numbers are getting larger. So we know it's divergent, but let's show for sure. So we're going to go 0.01 over 0.001. And we get that R is 10. So yes, R is greater than 1. So this is divergent. And for the last one, R is equal to T2, which is negative 0.25 over 0.5, and that gives us negative 0.5. So negative 0.5 is between negative 1 and 1, so this is convergent. Okay, so we're going to do example 2 on this video also. You've been asked to find the sum of an infinite series, and we're going to take our examples from our first example here. And we are going to use the ones from example 1 that are convergent geometric series. Okay, so that means the B, so 4 plus 2 plus 1. And our second one is D, which is 0.5 minus 0.25 plus 0.125 minus, and then dot, dot, dot. Okay, so we already know what our R value is for our first example. It's 0.5, and we know that it's convergent, so we can find a sum for it. So the sum for the infinite geometric series is T1 over 1 minus R. So T1 is 4 over 1 minus 0.5, and that gives us 4 over 0.5, which is 8. Okay, so our sum is 8 on this one. Okay, for the second one, we know that our our common ratio is negative 0.5. So S infinity is T1, which is 0.5 over 1 minus negative 0.5. Okay, which is going to give you 0.5 over 1.5. which, when you multiply both the numerator and the denominator by 10, gives you 5 over 15, which is 1 over 3. Okay, and we don't want to write our sum for this example as a decimal, because 1 over 3 gives you a repeating decimal, which is not an exact value, because you're going to have to round it off. So we're going to leave it as 1 over 3 because this is an exact number. Okay, so that concludes our little video for examples 1 and 2. Alright, so we're going to do example number 3, where you've been asked to find a common ratio. So the sum of this infinite geometric series is 120, and the first term is 18, and you've been asked to find the common ratio. So we know it's a infinite geometric series, and we are given that the sum of S subscript infinity is 120, and you're told that T1 is 18. So your formula for infinite geometric series is S subscript infinity is equal to T1 over 1 minus R. So in place of S subscript infinity, we put 120, in place of T1, 18, and that's over 1 minus R. Okay, so notice that your 1 minus R is in the denominator, so we are going to multiply both sides by 1 minus R, so we can reduce it on the right. And that leaves us with 120 times 1 minus R equals 18. Now, I'm not going to distribute my 120 over the 1 minus R, because it's going to be easier if I just divide both sides by 120, and that reduces on the left, so I'm left with 1 minus R, and then I'm going to divide 120 into 18, and I get 0.15. And so now I will bring my positive 1 to the right. It becomes negative, so I get negative r is equal to negative 0.85. And so r is equal to 0.85. In this next example, you are looking for values of x that cause the following infinite geometric series to have a finite sum. Now, because you know that this infinite geometric series has a finite sum, you know that it is convergent. So you know that your value for r is going to be between negative 1 and 1. Okay, so there's two examples here. I'll do the first one, and if you can do the first one with me, and then pause. I'll do the second one, and you do it on your own, and then come back to it once you've done it and see how you did compared to what I have on the screen when we get there. Okay? All right, so our first example, we have x plus 1 squared, and x plus 1 cubed. So notice that your terms are not actual numbers. You get algebraic expressions for each of them. So your first term is x plus 1, t2 is x plus 1 squared, and t3 is x plus 1 cubed. The best way to approach these questions is to come up with a value for r, okay, or at least an expression for r, because you know that this infinite geometric series is convergent, and so you know that r needs to be between negative 1 and 1. So it seems that r would be a good place to start, okay? So we're going to find r by going t2 over t1, so x plus 1 squared over x plus 1. And let's just write out the numerator as x plus 1 times x plus 1. And you can see that you can reduce 1x plus 1 from the numerator with the denominator, and that leaves you with x plus 1. So now you know that r is x plus 1. Now, because this is a convergent series, you know that r has to be between negative 1 and 1. So I'm going to take this value for r, which is x plus 1, and I'm going to substitute it into my condition for a convergent series. Okay? So what that gives me is negative 1 is less than x plus 1, which is less than 1. Okay, and now I'm going to solve for x. So I'm going to take this positive 1, and I'm going to bring it to the other side on the left, and it becomes negative 1. And when I do that, I'm going to have negative 2 on the left. And then I'm going to take this positive 1 and I'm going to move it to the right and simplify it with the one on the right of our inequality. And because the positive 1 becomes negative when you bring it to the right, you're going to have 1 minus 1, which is 0. Okay, so the value for x that will cause the following infinite geometric series to have a finite sum is that x needs to be between negative 2 and 0. Now, don't forget that with a convergent infinite geometric series, r cannot be equal to 0, okay? So what you need to do is you need to take your value for r here and you need to make it equal to 0 and find out what x is when x plus 1 equals 0. So we're going to solve for x here. So we're going to bring the positive 1 over to the right. It becomes negative. And so the condition is that x cannot equal negative 1. And so this is your answer for the first question here, that x has to be between negative 2 and 0, but it cannot be equal to negative 1, because if it was equal to negative 1, you would no longer have a geometric series. Okay? All right, so you might want to pause here and try the next one on your own, and then restart it once you've done and check to see how you did. Okay, so example 4b. X plus 2 is our term 1, x plus 2 squared is our term 2, and x plus 3 cubed is our term 3. We want to find out what r is, so we're going to go x plus 2 squared over x plus 2, right? So t2 over t1. We will rewrite our numerator as x plus 2 times x plus 2 over x plus 2. Reduce our x plus 2's in this expression, and we find that r is equal to x plus 2. Okay, keeping in mind that our r has to be between -1 and 1, I'm going to substitute this x plus 2 in for r. And so I get -1 is less than x plus 2, which is less than 1. So I want to bring my positive 2 over to the left. It becomes -2. -1 minus 1 is -3. And I want to bring my positive 2 over to the right also, and it becomes -2, and so 1 minus 2 is -1. Keeping in mind that r can't be 0, that means that x plus 2 can't be 0, so x can't be -2, so my x value has to be between -3 and -1, and x cannot be equal to -2, and this is your final answer. Okay, so that concludes example 4. Our next problem is an application problem. It's the bouncing ball problem, which is quite a common problem to work on with geometric sequences and series. In this particular example, a ball is dropped from a height of 10 meters, and after each bounce, it rises to 80% of its previous height. You're being asked to determine the total vertical distance traveled A at the exact moment the ball hits the ground at the 5th bounce, and B when it comes to rest. So the first part of the question, where you're asked to determine the vertical distance at the exact moment the ball hits the ground at the 5th bounce, is a partial sum question. Okay, and the second one, when the ball comes to rest, is considered an infinite geometric series question. All right, so here's a picture of what our bouncing ball might look like. Okay, and we're going to start at 10 meters. And it will rise to 80% of that on the next rise, okay, which 80% of 10 is 8. And then on the next one, 80% of that, which would be 6.4, and we could keep doing that, but it won't be necessary. Okay, bounces on this diagram are considered this to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Okay, another thing to keep in mind about our diagram is because we want total vertical distance, we've got the ball dropping and we also have the ball rising, and we need to calculate those distances. So I'll just draw in what we call our vertical drops in yellow. Okay, so this is vertical drop. Okay, and I'll do the vertical rises in blue. Okay, so because we're looking for a partial sum on A, we're going to use this formula. So S subscript n equals T1 times 1 minus r to the nth power over 1 minus r. Okay. Now we're going to break the first problem up into two parts. Okay, we need to calculate what our vertical drops are in terms of distance up to the 5th bounce, and we also want to calculate our vertical rises up to the 5th bounce. Okay, and we need to work them out separately. So we'll first do our vertical drops. Okay, so for our vertical drops, T1 will be our starting point, which is 10 meters. we can get r by dividing t2 by t1. So we get 0.8. And the number of vertical drops that we have up until the fifth bounce is 1, 2, 3, 4, 5. Okay, so n is 5. So we'll plug those numbers into our formula. We're looking for S5. That's equal to 10 times 1 minus 0.8 to the fifth power over 1 minus 0.8. And when you do all the math on that, you will find that your vertical drops have a total of 33.616 meters. Okay? And so the second part of this question is to calculate the vertical rises. Okay, now for our vertical rises, we're starting at 8 meters, so our T1 is 8. And our common ratio doesn't change, it's still 0.8. But n changes, right? If we're going to start here, then we've got 1, 2, 3, 4 vertical rises. Okay, so our n is equal to 4. So we're looking for S4. And that's equal to 8 times 1 minus 0.8 to the fourth over 1 minus 0.8. And when you do the math for that, you will get 23.616. Okay? So what's our total distance? Our total distance will be S5 plus S4. So 33.616 plus 23.616. And we get a total of 57.323. Okay? Now, some of you may have noticed that there is an easier way to work this out. If you can figure out what your vertical drops are, your vertical rises are 10 meters less than that because we just don't have this first 10 meter drop to consider, okay? So you can just figure out that your vertical rises will be 10 less than this, so 10 less than 33.616 is 23.616, and then you can add those two up to get the 57.323. Okay, so the total vertical distance at the fifth bounce is 57.323. Okay, so that takes care of A. Now for part B. Okay, now like I said earlier, B is a infinite geometric series question. Okay, we still have to break it up into two parts. We still want to do our vertical drops and our vertical rises. So we're going to start with our vertical drops. Okay, and remember that the formula we're going to use is the infinite series formula for the sum, which is S subscript infinity is equal to T1 over 1 minus R. Okay, so our T1 for our vertical drops is 10. Our common ratio is still 0.8, and our number of bounces, right, we don't have to know that, sorry. Okay, so this is all we need to know. All right, so S subscript infinity is 10 over 1 minus 0.8, and when you do the math on that, you should get 50, okay? Your vertical rises your T1 this time, okay, because we're starting here, is 8 meters. And your R is 0.8, We plug that into our formula. We get 8 over 1 minus 0.8, and we get 40. Okay, so our total is 50 plus 40, which is 90. Okay, and once again, there's a shortcut for this also, because if you figure out what your vertical drops are, then you just have to take 10 away from that to eliminate this first drop, and that will give you your vertical rises. So 50 minus 10 is 40, and then to get your total, you just add 50 plus 40, and you get 100, and so the total vertical distance is 90 meters. Okay, and so that includes this section, and it includes this unit on sequences and series.